Yeah, thank you. So I'm going to talk about stream processing with Ballerina. So what I'm not going to talk about, which we have not covered in the conference, is that we also have table support in Ballerina, like native table support. And how many of you have worked with any type of databases? All of you, right? How many of you know SQL? Almost all of you. So that basically means each and every one here know SQL. So why don't we use SQL in the native form within Ballerina so that you can easily program with a table? So the same concept we have brought in to the streams, because streams are also a form of table where we basically consume events and we process each row in a sequential manner. So when we get data, so at the source, all the data is an event. We collect all the data points and then we put into a table and then we can process them. At the same time, as and when the data come in, we can also do the processing in a streaming manner. So that is what the stream processing is. And it can also be used in various forms. Like, for example, we have looked at a lot of APIs and how APIs work. That is more of a request-response mechanism. But there is also a different paradigm, like there may be push, just you push the data in, you do some processing. If there is something interesting about it, you send it to a different person. So it is like all the message brokers and MQs are kind of built with that kind of data model. So we have to also support an event-driven kind of an architecture, and the stream processing also come in as a key component in enabling the event-driven architecture on your enterprise. So for example, if you want to build highly scalable event-driven systems, and for example, change data capture, real-time ETLs, notification management, and all of those comes into this particular domain. And I already explained about streams. So what we basically do, so we try to monitor something, detect anomalies, or else it can be real-time ETLs. Sometimes we want to monitor a particular stream, like for example sensors, and we want to calculate some sort of aggregation, like last 5 minutes, what has happened? Is there anything interesting happened that we need to alert? Or else, sometimes we might have a stock exchange stream coming in, and there are new streams coming in. Sometimes we want to correlate both and identify, okay, anything interesting happening in the stock exchange, that those companies are being mentioned in the news. So that may be useful for a financial market. And at the meantime, we also can understand very complex pattern. I'll go into the complex patterns in some time. So that is basically from the complex event processing domain. And at the meantime, we can also identify trends, like, okay, whether the temperature is continuously increasing. Like just KPIs are, I have a limit, and you will get to know at that point. But we also want to know the trajectory, like whether it's continuously increasing or there's a triple bottom. So all of those can be identified through complex event processing logics. So those are something that we can do with stream processing as well. So the key point is we have to process data forever. We are going to look at the data that is coming in, and we are continuously processing it. So how we can process that, and some of the key features of that is projection, like we get the data, we do some modification to that, and we send it out, which is a simple form. We do some filtering, we do some window and aggregations, like we can look at past 5 minutes or past 100 events, and we do processing. And also, when we are looking at fast 5 minutes, it can be a sliding 5 minutes, or it can be a tumbling 5 minutes, like 8 to 8.5, 8.5 to 8.10, 8.10 to 8.15. And within those periods, we can also do various form of aggregations, summing, count, min, max, whatever you name it. And at the same time, I also talked about joins, detecting patterns. So these are certain things that we are going to do in that. So if you want to build a stream processing language or logic, how you can do that? So one way of doing that is basically, okay, we implement language libraries, and we incorporate them, and we basically try to build something around it. That it is okay, it's easy because you are working with the same language that you learned. Like if Java, I mean, you have Java, okay, you just call Java services. We try to, loop several services together and kind of implement that, maybe possible. But it easily becomes very messy because you have to add callback after callback after callback, and it's going to be a mess. Okay, so there is an alternative way of doing this. Like, as all of you have already shown your hand, like you all know SQL. So SQL is an easiest way of getting a stream processing done, and that is what we have experienced so far. And in WSO2, we use this product called Stream Processor, which is also built based on a SQL-based model. But when it comes to SQL, there is a small problem. The stream processing logic, it is easy to implement in SQL, but there is also some other part that you have to do. Like, for example, we have to connect to external systems to get data in. We have to send some messages out. Sometimes we might need to retry. Sometimes we might need to do a load balancing logic. There can be all other stuff that comes into the play. So in those scenarios, currently what we are trying to do is we are trying to put annotations and work around it. But if you can write in a native language, it can solve your problem. So the solution for that is we are trying to blend the native programming language with the best of SQL so that you get best of both worlds. So whatever that you can do good in the normal programming language, such as connecting to external services, sending events, those are done in the normal way that you usually do. And when it comes to streaming and complex event processing or table manipulation, which an SQL can do better, we use SQL at that point. So for example, if you're going to do a small program, this is what you might do. So you might consume events from in Ballerina, like, okay, you can have an HTTP endpoint, somebody can send into that, or you can use JMS to consume from a MQ. We have Kafka and many other ways of consuming events. So when we consume the events, we have to convert them to a record. So that the record is a form of a table, something that we can put into a table. Like the same way that we can get a record and we can do some manipulation on that. So we convert the JSON or XML message into a record, and then we define SQL operation on that record so that we can identify some patterns or do some interesting things about it. After that, we create the output, which is a stream, and then we use our normal language to handle how they are going to send an email or SMS, whatever you want. You can use your normal Ballerina programming language, the native language, and continue. So let's take a simple scenario, and I'll walk through how we can solve this in the stream processing world. So when you have a lot of sensors, among the sensors, you want to find out some valid sensors, and then detect the sensors that have sensor reading greater than 10 in total within the last minute. So we are collecting some sensor reading around, and we want to, in a sliding manner, we want to just look at last minute, and the readings from that particular sensor should add up to 100. Okay? If that is the case, I am going to take some action about it. So it's a very abstract example. So let's see how we can code that. First of all, we have to have some records. So that is how we know what is the incoming data and what is the outgoing data. So here we have two records. One thing have a string name and the total, and the other one has the sensor data, which is the input. We have name and reading. Then we have to basically creating a normal Ballerina function which has streams in it. So these streams can be generated from the data that is coming in, which I'm not going to show in this example. But when the data comes in as stream, so the first stream is a sensor data, and the output stream is an alert stream. So we have two types of streams. And now we are creating a forever block that will run forever. So this is not something that we just run once. We have to always monitor the data, and we have to continuously run that. So, and this is a part of SQL that we are going to basically write to capture that and do the programming. So from the sensor data stream, where the reading is greater than 0, that means if there's a valid reading, then what I'm going to basically do is I'm going to look at this particular reading for last 1 minute, that is 60,000 milliseconds, and then I'm going to select the name, the sum of reading as total, grouping them by average, grouping them by name, and if that total is greater than 100, then I'm going to send an alert. So it is very straightforward to write this kind of logic in a SQL-ish way. So if you're going to write the same thing in a normal programming mode, it will be very difficult, like how you have windows and doing selects and aggregations, it will be a mess. So this is a much cleaner way of representing this problem and the way that we can solve this. So some more interesting queries that we can do. So here we have a scenario where we have raw materials coming in from one side, and then the production is happening on another side. So it's a just-in-time production. So as and when the raw material comes, people are going to get that and do production. So if the raw material input rate it has fallen below 5%, then to the rate of the consumption of production, then it may be a problem. So we have to alert and send messages to send more raw materials so that we can meet the production. So this is a simple forever block that basically does that. So we have a production input stream, and I'm going to just look at the last 10 seconds of that and the rate of consumption in last 10 seconds. And at the same time, we are joining that with the raw material stream. So this is similar to a join in table. So we can also do join in tables in a similar way, which we have not covered here apparently. And on a condition where the product name on the raw material and the production stream is the same, then I'm going to select the name, sum of amount of the total raw material consumption and the total production consumption, like raw material produced and the production consumption, grouping them by the name, and then I'm doing a small having calculation to make sure that it has not whether it has fallen below 5%. So this will give me an understanding of whether I need an alert or not. So whatever that comes in this particular error block is how you want to handle that particular error. You can call a function, you can send to an endpoint, and you can do any other processing that you need. Okay, so this is a very simple example of a pattern. So for example, if someone stole your credit card, they might go and try out whether that card works. If it works, then they might go to a store or buy it in Amazon, like you buy as much as you can and throw your card away. So if that is a potential fraud scenario and if you want to capture that, then we can write a pattern logic that you can do it like this. So this is what we are trying to capture here. So from every purchase in the purchase stream, where the price is less than $20, we call them as E1. This is followed by another purchase where the purchase is greater than 200, and that purchase, like the current purchase ID, is equal to the E1's purchase ID, which is the previous purchase that has happened some time back. And if both of these happen within 1 day, then I need the card ID, the initial payment, and the final payment amount as an alert. So identifying a particular pattern is not like writing this kind of stuff will need a lot of normal programming semantics, but this will basically help you to build a very easily composable, concise program that helps you to build the stream processing logic within Ballerina. So how you can use this within your system? Like stream processing like when you have external things coming in, that is one way that you can use stream processing to do it. But since you have stream processing inbuilt into your language, now you can monitor your own system by yourself. You don't need a separate system to monitor that. So we can process incoming messages or even locally produced events. So we have these observability tools. So we can do lots of observable features that we have embedded in that we are pushing all out. So all of those are also available as streams within the system. So we can consume our own system, like we can know what is how is my service behaving, and if my service is behaving badly, then the system itself, you can code how it should react. So you can build an autonomous system that can learn by itself and that can react on its own, which is very powerful, and we can't do without a streaming environment that is built into to your tool. So the second way of doing is like you can take a lot of local decisions without sending to a centralized place. Like for example, if you want to calculate some monitoring related information, you can do that monitoring related information locally within your system itself, and then you can send a summary to an external system. So you don't need to always send data to a different system for processing. And this also let you do local optimization without depending on an external system. So apart from that, it also gives you an advantage of doing stream processing or any type of analytics at the edge. So now, with the microservices architecture, now there are lots and lots of services. And if you want to monitor them or do any sorts of processing, if all of them are going to send events to a centralized place, then the central system is going to get very overloaded. So you can't basically handle it. So what this can basically do is each and every of those systems can do their local processing and send some summarized information, like even if it is metrics, observability, or even some business logic that we do, we can do local optimizations within that, summarize at the edge, and only if there is interesting events, then you can publish to the central system. So for example, if you are monitoring, if you have lots of sensors and you have lots of microservices monitoring the sensors, you don't need to send every 5 seconds. You can only monitor that, and if the temperature has changed more than a percentage, then you can then send an alert. Right? So you don't need to send each and every time. So you can do some pre-processing at the edge, and you can reduce the load to the central system, so you can be more and more intelligent going down the stream. So the initial ones will do basic filtering and simple kind of logic, and try to do local optimization and take decisions at the edge as much as possible, and then those decisions can be transformed further down so that ultimately you can do a centralized decision, and then we can have a loop back to the system as well. So this is highly scalable, and this let you run your systems much more independently. So those are the major features that we have, and on the roadmap, we are also making Ballerina. Currently, we have some of the stream processing concepts bind into a Java-based programming environment. Now we are bringing them into more and more Ballerina native programming, so that in future, if you want to do UDF, you can write a normal Ballerina function, and you can call that within the code. Like for example, if we have average, if you want to write standard deviation, you can write a standard deviation function in Ballerina. You can call within the code, so that, okay, when the data is streaming, the standard deviation is calculated based on your logic. So those kind of extensibility is being added currently. And this basically solves the problem that we usually have in the stream processing world, where you can't easily get UDFs into the systems, and this will basically solve that problem as well. And we are improving support with joining with the table, because as and when the data is streaming, we should also natively talk to tables, get more information from that, and we should be able to process that. And we are improving this query language even more. And if you want to run, so this is quite interesting, because microservices, some of the microservices, like almost all of them are in a stateless kind of an environment. But when it comes to streaming and process, or even some of those are really stateful system, right? So like business process or streams, all of those are stateful systems. So in those cases, we have to have a way of checkpointing. Like if the system goes down, there should be a checkpoint so that we can recover from that, and there should be a way of running in a high available mode. So current streaming in Ballerina doesn't support those, and we are working in progress to add the state recovery mechanism and supporting high availability in Ballerina. So those are some improvements that we are doing. And that's all I have for Ballerina, and I don't want to hold you back on your pizzas. Is there any questions? Yeah.
You showed the autonomous driving, but how does Ballerina play in that area at the edge?
So autonomous, I was not actually saying that Ballerina can autonomously drive a car. Eventually it will be probably, but not right now. So what I'm saying is, like for example, if you are building a system, right, and if you want to detect certain scenario, like for example, if your backend system is becoming slow, or if a database is there's a bottleneck, then how are you going to respond to the system? So maybe you can, if there are state, then you can save the state and shut down gracefully rather than going out of memory. You know, there you can do a lot of improvements like that. So you can monitor your system by yourself, and then you can take decisions locally rather than sending to external system and that firing events and a DevOps guy coming and looking that. So that is a particular example, but based on your business logic, we can customize that even further.